Marine engineering materials. In this module, we will be learning about marine engineering materials. The objectives are listed for your view. Iron ores are basic material used in the manufacture of various steels in the present use. In its natural state, iron ore may contain many impurities and vary considerably in iron content. Some of the more important iron ores are hematite, which contains 30 to 65% iron content approximately, and magnetite, which contains about 60 to 70% iron content approximately. Ores are first prepared by crushing, screening, and then sintering. Crushing produces even-sized lumps and fines. The fines are separated from the lumps by screening, and then they are mixed with coal or tar dust and sintered. Sintering causes agglomeration of the fines and coal dust due to application of heat, and also causes removal of some of the volatiles. The sinter, along with the unsintered ore, is fed into the blast furnace as part of the charge. The remaining charge is principally coke, which serves as fuel, and limestone, which serves as a flux. In the blast furnace, the charge is subjected to intense heat. The highest temperature is normally around 1800 degrees centigrade. At the bottom, carbon reacts with oxygen to give carbon dioxide. In the middle, carbon dioxide reacts with carbon to give carbon monoxide. And at the top, iron oxide reacts with carbon monoxide to give iron and carbon dioxide. The iron which is produced from this oxidation reduction action falls to the furnace bottom, melting as it falls and taking into solution carbon, sulfur, manganese, phosphorus, etc. When tapped, the molten iron runs from the furnace through sand channels into sand pig beds, hence the name pig iron. Pig iron is very brittle and has little use. An analysis of a sample is shown. To achieve the various forms of iron, pig iron has to undergo various processes. Let us briefly go through the various treatments and processes that are involved for conversion of acquired steel. Open hearth process. In this process, a broad, shallow furnace is used to support the charge of pig iron and scrap steel. Fuel employed in this process may be enriched blast furnace gas containing 30% carbon monoxide after cleaning. Bessemer process. In this steel making process, a blast of air is blown through a charge of molten pig iron contained in a Bessemer converter. The principal difference between open hearth and Bessemer steels of similar carbon content is brought about by the higher nitrogen content in Bessemer steel, and is also partly due to the higher degree of oxidation with this process. Coming to modern processes. Various modern steel-making processes have been developed and put into use. These include the LD, Caldo, rotor, and spray processes. The LD method of steel manufacture uses a converter similar in shape to that of the old Bessemer and is mounted on trunnions to enable it to be swung into a variety of desired positions. The Caldo and the rotor processes have not found the same popularity as the LD, even though they are similar in that they are using oxygen for refining. They both use converters which are rotated, and the process is much slower and more expensive. BISRA, that is the British Iron and Steel Research Association, have developed a process in which the molten iron running from the blast furnace is subjected to jets of high-speed oxygen that spray the metal into a container. This gives rapid refining since the oxygen and the metal intimately mix. The main advantages with this system are that the intermediate stage of carrying the molten metal from the blast furnace to the steel making plant is eliminated, and the steel production rate is increased considerably. Metallurgy of cast iron and steel. In order to understand the metallurgy of cast iron and steel, we need to have a basic understanding of the iron-carbon equilibrium diagram. The iron-carbon equilibrium diagram is a graph with percentage carbon along the x-axis and the temperature along the y-axis. This representation gives us the various forms of iron and its changes over temperature with varied percentage of carbon in it. Carbon can exist in two states, crystalline and non-crystalline. In the former state, diamond and graphite, and in the latter, it is pure carbon. Pure iron, which is ferrite, is soft and ductile with considerable strength. When carbon is added to the iron, it combines with it to form a very hard brittle compound. This compound of iron and carbon, called iron carbide or cementite, lies side by side with ferrite in laminations to form a structure called pearlite, so called because of its mother of pearl appearance. As more carbon is added to the iron, more iron carbide and hence more pearlite is formed, with a reduction in the amount of free ferrite. When the carbon content is approximately 0.9%, the free ferrite no longer exists, and the whole structure is composed of pearlite alone. Further increases in carbon to the iron produces free iron carbide with pearlite reduction. The steel range terminates at approximately 2% carbon content and the cast iron range commences. Carbon content for cast iron may vary from 2% to 4% approximately. This carbon may be present in either the form of cementite or graphite, depending upon certain factors, one of which is the cooling rate. Grey or malleable cast iron is composed of pearlite and cementite, which gives white cast iron. This is brittle and difficult to machine and hence does not normally encounter much use in marine work. Cast iron is produced by remelting pig iron in a cupola. It's a small type of blast furnace wherein the composition of the iron is suitably adjusted. The fluidity of the material makes it suitable for casting. Other properties of cast iron include machinability, wear resistance, and high compressive strength. Properties of materials. The choice of a material to be used as an engineering component depends upon the material's engineering and mechanical properties. The major mechanical properties are ductility. It is that property of a material which enables it to be drawn easily into wire form. The percentage elongation and contraction of area as determined from a tensile test are a good practical measure of ductility. Brittleness. This can be defined as lack of ductility. Malleability. It is a property similar to ductility. If a material can be easily beaten or rolled into plate form, it is said to be malleable. Elasticity. If all the strain in a stressed material disappears upon removal of the stress, the material is said to be elastic. Plasticity. If none of the strain in a stressed material disappears upon removal of the stress, the material is considered plastic. Hardness. A material's resistance to erosion or wear indicates the hardness of the material. Strength. The greater the load which can be carried, the stronger the material. Toughness. A material's ability to sustain variable load conditions without failure is a measure of a material's toughness or tenacity. Materials could be strong and yet brittle, but a material which is tough has strength and resilience. Heat treatment of carbon steels. Let's begin with hardening and tempering. When iron is heated to its melting point, two arrests occur wherein there is heat absorption. The temperature at which these arrests occur are called critical points. At these critical points, considerable changes of internal structure takes place, and therefore different physical properties are available if these structures could be trapped. With steel, these changes in the internal structure of the iron at the critical points affect the carbon which is present in the form of iron carbide. At the upper critical temperature range, that is 720 to 900 degrees centigrade, in the solid state, the iron structure formed has the ability to dissolve the iron carbide into solution, forming a new structure. If at this stage the steel is suddenly quenched in water, the iron carbide will remain in solution in the iron, but the iron structure will have reverted to its original form. This completely new structure, which has been brought about by heating and then rapidly cooling, is called martensite, a hard needle-like structure consisting of iron supersaturated with carbon, and is basically responsible for hardening steels. If a steel of approximately 0.4% carbon content is heated to a temperature above its upper critical, that is about 800 degrees centigrade, and is then suddenly cooled by quenching, its Brinell hardness numeral would be increased from approximately 2000 to 6000. In this condition, steel would be fully hardened, that is, fully martensitic. Choosing a temperature lower than the above, but not lower than 720 degrees centigrade, and then quenching will produce a partly hardened steel having a Brinell numeral between 2000 to 6000. Hardening material in this way produces internal stresses and also makes the material brittle. To relieve the stresses and restore ductility without loss of hardness or toughness, the material is tempered. Tempering consists of heating the material to about 250 degrees centigrade, retaining this temperature for a duration of time. Now, this depends on the mass and the degree of the toughness that is required, and then quenching or cooling it in air. The combination of hardness and tempering is greatly employed with steels and alloy steels. A wide range of properties is thus available thereby. Components such as drills, chisels, punches, saws, reamers are invariably subjected to the above process. Straight carbon steels whose carbon content is below 0.2% are not usually subjected to hardening and tempering processes. Annealing and normalizing. This process consists of heating the material to a predetermined temperature, possibly allowing it to soak at that temperature and then cooling it in the furnace at a controlled rate. For full annealing and normalizing, the temperature for carbon steels is usually 30 to 40 degrees centigrade above the upper critical temperature. The objective of annealing is either to grain refine, induce ductility, stress relief, or a combination of all of these. Castings, forgings, sheets, wires, and welded materials can be subjected to an annealing process. Normalizing is similar to annealing, but the difference between full annealing and the normalizing process is that in case of annealing, the material is cooled slowly in the furnace, whereas for normalizing, the material is cooled in still air outside the furnace. These processes of full annealing and normalizing are mainly used on castings, since they will usually have a variation in size and shape of grain. The casting is heated to about 40 degrees centigrade above the critical temperature until it is uniform in temperature throughout. Then it is cooled. This produces a uniform grain structure with increased ductility. The more rapid cooling of the casting that occurs with normalizing gives a better, closer grained surface finish. Black heart process. The castings are placed in airtight, heat-resistant metal containers and heated up to 1000 degrees centigrade. They are kept at this annealing temperature for up to 160 hours or so, depending upon material analysis. The prolonged heating causes breakdown of the cementite to give finely divided temper carbon in a matrix of ferrite, which has a black appearance and hence black heart. For high carbon castings, example 2.5% content of carbon, the black heart process may be used to produce a softer, ductile and more easily machined component that would be similar mechanically to cast steel. Flame hardening. This process is used for increasing the surface of hardness of cast iron, steels, alloy cast iron, and alloy steels. With the increase in surface hardness, there is high improvement in wear resistance also. To flame harden a component, for example gear teeth, an oxyacetylene torch is used to preheat the surfaces of the metal to a temperature between 800 to 850 degrees centigrade. A water spray closely following the oxyacetylene torch quenches the material, thereby inducing hardness. Care in operation of this process is essential because overheating must be prevented. Case hardening. This is sometimes referred to as pack carburizing. The steel component to be case hardened is packed in a box which may be made of fire clay, cast iron, or a heat-resisting nickel iron alloy. Carbon-rich material such as charred leather, charcoal, crushed bone, and horn or other material containing carbon is the packing medium, which would be encompassing the component. The box is then placed in a furnace and raised in temperature to above 900 degrees centigrade. The surface of the component will then absorb carbon, forming an extremely hard case. Gudgeon pins and other bearing pins are examples of components which may be case hardened. They would possess a hard outer case with good wear resistance and a relatively soft inner core which may retain the ductility and toughness necessary for such components. Spheroidizing anneal. Spheroidizing of steels is accomplished by heating the steel to a temperature between 650 degrees to 700 degrees centigrade, when the pyritic cementite will become globular. This process is employed to soften tool steels in order that they may be easily drawn and machined. After shaping, the material is heated for hardening and the globules or spheres of cementite will be dissolved. Other treatments include work hardening, induction hardening, and nitriding. Let's discuss the effects of alloying elements. Addition of nickel increases strength and erosion resistance. It does not greatly reduce ductility until 8% nickel is reached. A low to medium carbon steel with 3 to 3.75% nickel content is used for connecting rods, piston and pump rods. Addition of chromium increases grain size, induces hardness, improves resistance to erosion and corrosion. This element is frequently combined with nickel to produce stainless steels and irons which are used for such items as turbine blades, pump rods and valves. Addition of molybdenum is used to increase strength, especially employed for increasing strength at high temperatures, which is one reason why it is used for superheater tubes, turbine rotors, etc. Another reason for its use is its action in removing the possibility of embrittlement from those steels which are prone to embrittlement. Addition of vanadium increases the strength and fatigue resistance. It is used in conjunction with molybdenum for boiler tube materials. Non-ferrous materials. Some of the most commonly used non-ferrous materials on board are copper, brass, bronze, aluminum, copper nickel, white metals and titanium. Copper. This material is used extensively for electrical fittings as it has good electrical conduction properties. Brass is an alloy of copper and zinc, usually with a predominance of copper. When brasses are in contact with corrosive conditions, either atmospheric or seawater, they may dezincify, leaving behind a porous, spongy mass of copper. To prevent dezincification, an inhibitor is added to the brass. One such inhibitor is arsenic. Brasses in marine use include valves, bearings, condenser tubes, etc. Alloying elements such as tin, aluminum, and nickel are frequently employed into improved brasses. Bronze is an alloy of copper and tin, but the term bronze is frequently used today to indicate superior type of brass. It resists the corrosive effect of seawater, has considerable resistance to wear, and is used in many marine fittings. With the addition of other alloying elements, its range of use becomes extensive. Manganese in small amounts increases erosive resistance, forms manganese bronze. Propeller brass is the most widely used term in marine usage, which itself tells the significance of its usage. Aluminium is progressively supplanting other materials in use for specific items in the marine industry. It resists atmospheric corrosion and its specific gravity is about 1/3 that of steel. In the pure state, its strength can be raised to equal and even surpass that of steel without great loss of ductility. In this form, it is used extensively for structural work. Copper nickel. Cupronickel alloys have considerable strength, resistance to corrosion and erosion. The 80-20 or 70-30 cupro-nickel are used for condenser tubes as they strongly resist the attack of estuarine and seawater. A well-known alloy, Monel metal, composed of approximately 2/3 nickel, remainder principally copper, is used for turbine blades, pump rods and impellers, scavenge valves and superheated steam valves. Monel metal retains high strength at high temperatures. With the addition of 2 to 4% aluminum, forming a material known as K-monel, it can be temper hardened, thus its strength can be increased still further without detracting from its other properties. White metals. White metal bearing alloys may be either tin or lead-based materials containing antimony and copper or antimony alone. Tin-based white metals are sometimes referred to as Babbitt metals because of their good bearing surface and uniform microstructure. Titanium. Ideal where resistance to erosion and impingement corrosion are the most important requirements. It is virtually completely resistant to corrosion in seawater. Only under exceptional conditions of erosion would the protective oxide film be damaged. When alloyed with about 2% of copper, a moderate increase in strength results. It is widely used in heat exchangers, especially the plate variety type. The non-metallic materials used widely on board the ships would be plastic polymers, nitrile components, PTFE, epoxy resin, cotton, and silicon nitrides. The other topics which we are supposed to be covering in this chapter are welding and gas cutting. We will go in detail on these subjects in our third chapter of fabrication. So let's move to our next topic.